the first set of functions, and those are what we call the algebraic functions. Meaning functions we can obtain simply by taking variables and adding constants to them, multiplying, taking and raising to powers, dividing by terms with variables, taking square roots, taking absolute values, performing algebraic computations on them, and building them up and building these complicated functions. Now, arguably, the most important ones for you guys are going to be the polynomials. So we're going to learn them very well. They are used all throughout. So really focusing on the polynomials. Rational functions are actually, can be much more powerful because they are so unwieldy, you saw all their graphs going all in different directions, it's hard to understand and make sense out of it. Whereas polynomials we can easily analyze with them. Now, they allow us to do certain things, certain phenomena. For example, we can look at things that are, parabolas. We can look at linear phenomena. We can look at things that go up as a square root. We can even look at some of these more elaborate, phenomena that we're looking at, something like that, or even something like this. So we use these functions to kind of model phenomena in the world. A lot of phenomena may take the shape of a parabola. A lot of data we look at in the real world, we have data and we plot it to a straight line and we look at trends. But there are certain types of data that we cannot model with either or any of the algebraic functions that we've given. And there's even still, you might have something that has an absolute value. It always stays positive. Sometimes it's decreasing and sometimes it's increasing. But the whole purpose of functions is to model things in the real world so we can understand about them. So we want to choose a variety of different functions that will give us shapes to model things out in nature, or even things that are not nature but can be, human-made, and they follow certain features. Well, because there's another type of phenomena that exists, and here's two such phenomena. There's one phenomenon that goes like this. Now, you think it looks similar to this, but we're going to find that it's not at all close to that. There's one phenomenon that goes, and this is essentially what everyone was worried about with our spread of COVID-19, and this is what we call exponential change. And it's sometimes you'll see it look like this, and we'll go from here. We're not going to look at this course. This is a sigmoid shape. You can't get this with any polynomial, and you can't even get it with any of these rational functions. That's one class of functions. And there's another one that's kind of related to that kind of goes like this way. But there's also another class of functions that we can't do, and those are things that kind of go like that. Cyclical, periodic functions. Very important as we look at cycles. Now, this is extremely important if you're going to go into engineering and you want to look at current, AC current, it runs in cycles. We need a new class of functions that is not algebraic, that we can reproduce that sort of a shape to use it to model things in the real world. And those different types of functions are called transcendental functions. And that's what we're going to be looking at. And Chapter 3 is all about this new class of functions called transcendental functions. They kind of transcend the basic algebra. Transcendental function. Now, we could try and make a definition where we specifically tell what a transcendental function is, but any definition we try to create, it's not going to be correct. So the easiest way, and it's kind of a simple definition, is this. Here's our definition of a transcendental function. It's, a transcendental function is any function that's not algebraic. That's all it is. Transcendental, it's either algebraic or it's transcendental. It transcends the algebra. Transcendental function. So a transcendental function is not algebraic. Meaning I can't create it with a finite number of multiplications or additions or something like that. Transcendental functions actually involve this concept of the infinite. For us to obtain transcendental functions, we have to incorporate infinity. And that's a really strange concept into that. Incorporate this concept of the infinite, we can create these new types of functions that will allow us to model some of the other things in nature and the world. And that's what we're going to be doing. Now, I'm going to give you the overview of the types of transcendental functions we're going to look at. We're not going to look at all of them, just a couple of them here. And they're really the important ones. The first types of transcendental functions we're going to do are the trigonometric. Things such as the sine, the cosine, and the tangent, those sort of things. We'll identify those, trigonometric functions. They will allow us to handle periodic and repetitive, if you will, phenomena. And we're going to find, just like early on in the beginning of the book, we talked about a function and its inverse, there's also going to be related functions to the trigonometric function called the inverse trig functions. And we'll look and introduce those. In addition, we want to talk about the other phenomena I put up there, and these are exponential functions. And we'll define those later on, not right now, but in a few days we'll be looking at exponential functions. And the inverse exponential are given a special name, and they're called logarithms. We have the inverse exponentials, also called logarithmic functions. So we're going to look at these over the next few days, exponentials, logs, and trigonometric functions. We have to introduce a lot of new terminology and new concepts and ideas to be able to understand them. But we'll be doing that, and again, we'll also be carefully looking at the idea of the domain and ranges. And then also some very basic properties, which we will add to throughout the course. The way I set this course up, I wanted to introduce all of the functions early on, and then build upon them, repeat on them over and over again, until we build up all of our functions with all the properties and all the tools we need to analyze them. So trig functions are not algebraic, exponential and logarithmic functions are not algebraic. They actually have this concept of infinity built into them. And you'll see, I'll show you where, in many cases, especially when we're looking at the Euler number E, where that comes and incorporates the concept of infinity. Okay, any questions? So let's start with our first type of functions, transcendental functions, I should say, called trig functions. But before we jump into that, we're going to need to kind of develop some basic new tools and concepts. So this is in essentially 3.1 and basic trig functions. Now, we're going to develop them not using right triangle trigonometry. I'm purposely going to develop them in a different way. Most of you are used to them in terms of SOHCAHTOA and things of that nature. Yes, Marino.
Sorry, that was my cat.
Okay. Did your cat ask a question?
No.
Maybe it did. I don't know. That's why. That's another reason for not just showing videos. Awkward situations can happen. So, okay. So we're going to look at some basic trig functions. A lot of you probably remember with right triangle trigonometry and that, development of it. We're not going to do it that way. Not that there's anything wrong, but we want to emphasize the fact that what we are trying to do with these types of functions, we're trying to model, if you will, cyclical behavior. So we want to emphasize this cyclical behavior of things. Meaning, and the most obvious thing to represent cyclical behavior is a circle. So we're going to be using a unit circle, and we're going to see there's a lot of power in this, using this concept of the unit circle to define and show some basic ideas and connections of these basic trig functions. So that's what we're going to be our focus. But we will introduce right triangle trigonometry later on, but we're not going to define them using our right triangle. Well, you have, A, B, and your hypotenuse C, or, you have some angle here. We're going to talk about that in a minute. So this is the right triangle way of approach of defining them. Now, if you know this, that's good. But try and, not always think in this way. Try and think in this new way to give you a different perspective on where they come from and how they develop. Okay, before we jump into defining these functions, we need some basic concepts. The first concept we're going to look at is how do I measure something called an angle? Screen the break. And I can move this back or something like that. Maybe sometimes the chair may hit that. Is that better? Let's see what's going on. Is that any better? Can you see more of that now? Hopefully.
I think it needs to be moved the opposite direction.
Oh, the opposite direction? So moving forward, you mean?
Yeah.
Yeah. Because I can't say, I've seen just a little tiny bit. What I could also do is just simply angle it just a little bit further that way.
The other way. The other way.
Oh, the other way. It's not seeing that end. Okay.
Right, exactly.
Yeah, it's not to see. It's a little tiny picture I'm looking at on my computer screen. I can barely see it. Oh, I could just move it back a little bit, and hopefully it captures it there. That helped a little bit. Everyone see the entire screen now?
Yeah, you're all
Okay.
good. Yeah, you're all good.
Good. Okay, so we're going to talk about this concept of an angle. And what is that? Well, that's the relative orientation of two intersecting lines. And this is going to give us the relative orientation of two intersecting lines. I have a line here and say a line there. And they intersect at some point, and we'd like to measure this relative orientation with respect to each other. That we're going to define as an angle, and we're going to use the Greek letter, a lowercase Greek letter called theta. A little lowercase Greek letter theta. Now, there are two ways to measure this. So there's two approaches. One approach is we can use the degree measure. And I'm going to derive and give you both of them. We can measure an angle in degrees, and when you get to calculus, you're going to also measure in this concept of radians. Now you may have noticed on a lot of your calculators you have a degree or a radian mode. And we're going to talk about that, very quickly and understand that. So how are we going to do that? Okay, let's start with degrees. That's the easiest. Most people, men and women on the street, they understand the degree measure. And let's kind of set up for our measurement in degree mode. So here's the degree measure. Now, nobody knows for sure, but it was determined that if you want to go complete one cycle around, so if I go from, here's my point over here, this is what I call my reference side. So that's the reference side. Reference side, or line, if you will. And if I want to measure an angle that goes all the way around, that goes and just sweeps it all the way around, and that angle theta, it was determined to let that angle, a complete cycle around, to be equal to 360. And to represent a degree, we've used a little superscript, a little circle, 360 degrees. Now, the question that often arises is, why? Why 360? Well, a couple of reasons have been speculated on. One is it's very close to the number of days in a year. We go through 365 and a quarter, so it's close to 360, but 365 is not a nice number. It turns out that 360 is a really nice number because you can break it into 2 pieces without any remainder, 3 pieces, 4 pieces, 5 pieces, 6 pieces, 7 doesn't work. 8 works, 9, 10. You can break it into a lot of different, divide it by a lot of different parts and not have fractions or decimals. So it's kind of a nice number. For whatever reason, we could have chose 100 and everything would have been based upon that. But 100 isn't as nice because you can divide 100 into, 2, you can divide it into 3, 4 works, 5 works, 6 doesn't. So 360, for whatever reason, not sure, is it related to the fact that we go through a cycle, 360 days in a year, and our calendar comes back and starts repeating itself, perhaps? Or is it that 360 is a nice number for dividing it up into sub-pieces? But for whatever reason, we take that as our starting point. If I make one complete cycle around, the angle I would make would be 360 degrees. Then, once we're given that, we can develop and derive all of the other angles in a similar fashion. So that's the beginning point. And then you might have, for example, say a line that goes this way and a line that goes that way. And this angle here would be 1/4 of that 360, or 90 degrees. Very simple. Some common angles, if you will. There's the first one, 360, 90, and you can do any fraction of that. For example, I could come over here and do halfway between my 0 degrees and 90 degrees orientation. And this might be half of the distance through that, and we have theta is 45 degrees. And you can keep going. You can go over here. If I go one line here and the other line the opposite direction, you can see that angle there is 180 degrees. Move it down, I go 270, and I can come back over here and do 315 over here, keep going around and back to 360. Now, once I hit that 360, I can either start counting again or just keep adding to it. For example, I could go around instead of one time, there's one time around, but I don't stop this, I go 2 times around. Well, in that case, that angle I make there is now double the 360, or 720 degrees. Okay, So if we go in a counterclockwise fashion, notice all these lines, all these arrows, if you will, are drawn in a counterclockwise. Fashion. Our angles are positive. We consider that to be a positive angle. But we don't always have to go in a counterclockwise. We could, if we wished, turn around and do it clockwise. And you'll see some of the connections. This is what can be confusing. So say I drew a line here, and then one down here. And say I started at my reference line, and I went in this direction. So instead of going counterclockwise, I chose to rotate this in a counterclockwise fashion. So this angle, theta, would be equal to a negative 90 degrees. But interesting to note over here that if instead I chose to go in a clockwise fashion, went all the way around over here, this other angle, I'll call it theta as well, it's a different theta, it's 270 degrees. So they give you the same result. So these two angles are equivalent to each other in the sense that they give you the same location, and they give the same orientation of those lines. One measured in a counterclockwise fashion and one measured in a clockwise. So anytime you go clockwise, always put in a negative value. You can see it gets important as we go later on. Okay, so I'm assuming most of you are pretty good with your angles, that you know your angles in degrees, degree measure. Where you may be a little bit off is interpreting this now in terms of a different sort of measure, something called the radian measure. This is now where we go to our unit circle, and that's how we're going to do it. Because you may be noticing I'm drawing these lines going around this, they're circles. So that naturally says, let's go and measure or create a new metric or a new measure for our angles, and we're going to use the radian measure. So most of you are fairly comfortable with the degree measure, I'm assuming. We've seen it before. Radians may be a little bit foggy in your minds. It's a different way of measuring an angle. So let's take a look at the radian measure. And just as I said earlier, we're looking at that unit circle. So here's our circle, a circle of radius 1 for now. Doesn't have to be 1, but for us, we'll just take it as 1 for now. And we start with our reference side over here. So here's our reference. At the center, we have our reference side. Something to reference our angle from. And say we come over here and we form an angle, kind of move over here, and we call that angle theta. Well, instead of measuring in degrees, degrees would be that measure of that angle over here. For the radian measure, we measure a length, not a degree measure, but a length. We are going to connect the measure of that angle theta with the length of that arc. So radian measure measures this length. And again, this is our unit circle. So it's a circle here of radius 1. This distance here has a distance of 1, r equal to 1 in our circle. So let's make note of that. Now, if I go completely around the circle, that's the circumference. So what is the circumference circle of radius 1? Let's take a look at that. So going one complete cycle around, so one complete cycle around, is the distance is equal to the circumference. And remember, our circumference is, 2 pi times the radius r. Well, our radius is a unit circle radius 1, so that circumference, that distance is 2 pi units. No longer a degree measure, it's 2 pi, which is the length that I would travel if I were to move along that unit circle. That's what radian measure is. It's not degrees, it's the length of that distance along that, whatever that angle is along that unit circle. So let's put up a few common angles over here and just kind of see what we have. I'll kind of come over here and let me give you a couple of common angles. So say here I am, and I've put this angle over here. And in this case, I'm back my unit circle, so I want this distance right here. What angle theta is that? Sometimes you put it down here and say, okay, what is that measure of that angle theta? So what is that angle theta? In terms of degrees, we know it's 90 degrees. But in terms of radian measures, well, that's instead of 2 pi units around, it's 1, 2, 3, 1/4 of that. So over here, this is just pi over 2, because I take my 2 pi, which is the distance all the way around, and I divide it into 4. So this is actually equal to, in this case, pi over 2, because that's the distance I would travel. 3.1415 divided by 2, so it's like 1.6 whatever units around, and that's what it is. That's a common angle. We know that as a 90-degree angle. What if I go completely to the other side? This is one version of this. Here's another version of this. I start here, in a circle, and I end up over here, meaning I went around one, if you will, complete cycle. So I went half the distance around. So this angle here, that angle there, is equal to pi units. And then if I continue to go around, each of these little pieces is pi over 2 gives pi. But I could keep going around that circle if I wanted to. And here's, make it black, too many colors here. So I go this way. I'm still on that unit circle, so I go from here all the way around over here, come over here. In that case, that's pi over 2, another pi over 2, another pi over 2. This angle of that measure, theta, is 3 pi over 2. Then I come back one more pi over 2 to 4 pi over 2, which is 2 pi. So that's how you measure in increments of the distance around a unit circle. Not a degree measure, it's an actual number. Now, it follows the same process that if you rotate, this is all counterclockwise giving me negative angles, but if I came down here and I decided to rotate this in the opposite direction, like I could over here, so if I go this way, what would that be? Well, that's a negative pi over 2. Okay, so we have two ways to measure an angle, and you have to be careful about that. Because if you look at your calculator, yes, Annie?
I remember my high school class, my teacher told me, like, with this concept in particular, because I guess the radian term was hard for us. So he said we could do, like, an equation where it's like if you multiply the degree times like pi over 180, then it gives you a good.
Yeah, I'm going to show you how to, that's coming up. I just want to introduce, I'm going to show you how to translate between the two.
I don't know if you were able to do that.
Yep, I'm going to do everything. This is, at first, I'm doing everything from scratch, meaning this is what they are, then we want to switch from one to the other. But I want to make mention now, before we go into anything about when you're on a calculator. This is where it's very critical that you're using the correct measure of an angle when you work a problem. Otherwise, you'll get totally different answers, and one will be totally wrong. So here's our calculator. If you come in over here, It's so critical when you look at the mode button over here. And down here you see radian and degrees. That's where it's going to be critical. When you are using radians, and that's predominantly in the calculus you use radians. Once in a while you switch to degrees. Here we're going to use both. So we're going to have to know when to hit the radian button or when to come over here and move it and hit the degree button. You're going to get totally different answers if you don't have the right measure of the angle. So this is where a lot of times people get screwy answers. This is where it happens. They didn't change their calculator to radians or degrees or vice versa. But what you just mentioned is, how do we go from one to another? We have two measures. They're both important. Radian is much more important in the calculus than the degree measure. Degree measures is very important in a lot of the engineering things we do, because you measure a lot of different, we use right triangle, and especially when we get to right triangle trigonometry, we'll be doing that. So, as you mentioned, what's the connection between the two? Well, we kind of have that from the beginning of this. So we'd like to connect the degree with the radian measure. But what we know is if we go one complete cycle around, so here we are, we go one complete cycle around, in degrees, that's equal to 360 degrees. And the radian measure, and radians if you will, one complete cycle around is the distance we go around here, that is equal to 2 pi radians. So we set the two equal to each other. That's a connection. We say that 360 degrees is equivalent to, they're not equal, it's an equivalent measuring, or metric if you will, of 2 pi. Or you can divide both sides by 2, and you get that 180 degrees is equivalent to pi. I'm going to write the word radian to know that they're different. Typically, we don't write the word radians, but that is there without our saying it. It means pi radians. We can use this to create, if you will, a conversion factor. So this can be used. So this can be used to create a set of conversion factors. Let me do that. Conversion factors. So what I can do is I can divide both sides of this by 180 degrees, and I get pi divided by 180 degrees. If I do that from this, that's equal to 1. They're equivalent. They're equivalent metrics. This factor here will convert from degrees to radians. The degrees will cancel. So if I do use this factor, this converts from degrees to radians. Well, instead I could divide both sides by pi if I wanted to. So I could turn around and write it like this. 180 degrees over pi, that still is equal to 1 according to this, just dividing both sides over here by pi. This, however, will allow us to convert from the radian measure to degrees. And I'll show you exactly why and how it works. Okay, so let's see about how we do some basic conversions over here. So say, for example, someone says, okay, I'm going to do some conversions. So I have something that I have an angle in degrees. I have 45 degrees. And I want to convert those into my radian measure. So I want to find out, how many radians that is. So I'm going to use my conversion from degrees to radians. Let's plug it in. So I put my 45 degrees. I'm grabbing my conversion factor, which is pi over 180 degrees. Now, how do I know I'm using the right one? Well, just like in algebra, if the same unit is in the numerator and denominator, they cancel out. So you know you're doing it correctly because this degree will cancel with that degree and give me just my radian measure left. So this is now equivalent to 45 over 180, or 40 pi. Let me just move the pi out. I can do that. And then I can simplify this. So I can divide top and bottom by 45, and you can see this is equivalent. If I divide this by 45, I get 4. So this is equivalent to, in fact, let me do it. Well, in fact, even if you don't do it, say we did this. Let me just simplify. I have my pi out here. Put my pi out here, and we're going to simplify this a little bit. Pi will come down. I can divide everything by 5, because I have a 5 and a 0. So that gives me 9 times 36. And I could divide top and bottom by 9, so I end up with 1/4. Or I could have divided everything by 45, top and bottom. So this now becomes pi over 4. And that's my radian measure, pi over 4. Let's take a look at another one. Say I have, in this case, pi divided by 3, no degree symbol, and that's radian, so I'd like to convert that into some measure in terms of degrees. Well, now I'm going to use this formulation over here. Okay, so what would I put? That's pi over 3 times, now I have 180 degrees over the pi radians. This is a radian, and this is a radian, so the radians cancel out, and the pi's cancel out. So it's 180 over 3, which is just 60, and the units are degrees. Now, sometimes you can simply, if you see a pi, the other way of doing it, if you see a pi, replace pi with 180. That's an alternative way of doing it. If there's a pi, you can, every time you see a pi, you just plug in 180 for the pi. That's essentially what you're doing with this conversion. Because we already know that pi, that's how we got this relationship, is equivalent to 180 degrees. And different metrics, but they give you the same equivalent answer. So I could put 180 divided by 3 is 60. That's sometimes a quick way of doing it in your head. But you have to be careful. For example, what if I gave you this? This is where you will mess up. Try this and tell me the answer you get. And I'll see if you understand what I'm talking about here and now. So here's another problem to try. Say I have pi degrees. Can you tell me what my answer is in radians? What's the equivalent measure of that in radians? If you're going to get a strange answer, if your answer looks bizarre, it's correct. If it doesn't, you made a mistake. My final answer should be pi squared divided by 180 radians. Does anyone want to see how I got that? Anyone okay with that? Okay, let's do it. Because what it is, that tells me I'm in degrees. Pi does not tell me I'm in radians. That is equivalent to approximately, this is approximately, 3.1415 degrees. A little over 3 degrees. That's what it means. Well, I want to go from my degree measure to radians. So I want to go from degrees to radians. So I have to use this. So I start with pi degrees. And I'm going to multiply by my conversion. So the degrees has to be down here to cancel with that degree. So it's 180 degrees over pi. That's my conversion factor. What do I do over here? Well, I can cancel out the degree measure. Degrees on the top, degrees on the bottom, numerator, denominator, they cancel. It's no longer in degrees. It's now switched over to radians. So I just multiply through pi times pi gives me pi squared all over 180. So you have to be a little bit careful. Definitely have to be careful. What if I gave you something like this? So I have, 5 radians, and I want you to tell me how many degrees is that? Notice there's no pi in that, so I can't use that. So how many degrees is 5 radians? And hopefully you try it yourself, and I'll put the answer over here. It's 900 divided by pi degrees. And pi is 3.14, so 900 divided by 6, Anyone want to see that one? Yes, Ashley.
So I got the right answer, but should we assume that if there's no degrees symbol, that it's always going to be a radian when we're doing
That's
that?
right. You have to assume that. If there's no degree symbol, it has to be radian. Here, I emphasize that that degree was not there. That would be pi. That would be 180 degrees. But because it's degree measure, if there's nothing there, it's always radians. Because we're going to see these numbers. And that's what you see in the real numbers on the real number line. They're all in radians. They're not in degrees. So yes, you have to assume no degree symbol. It's in radians. So I'm going to convert from my radians over here to degrees. So I start with my 5. And I could write radians if you want, just to kind of emphasize. And I'm going to use my conversion, 180 degrees for every pi radians. And what cancels out is a radian measure there. And that's 5 times 180 is 90 over pi, and the units are now degrees. Put that in because a lot of people make mistakes with that. It's confusing. Any questions on that so far? I'll have you work some problems in the homework. The last thing I want to end with, there's no homework problems on these, but in the last few minutes, I want to introduce another important construction that we will need and will help us in working our and deriving our trig functions. We all know that when we graph, we all learned about the rectangular or Cartesian coordinates. We all learned rectangular, sometimes they're called Cartesian coordinates. And we get a grid. We've been doing that all along, our X and our Y. And we have a little rectangular grid going on here. So constant X values and constant Y values. Everyone's comfortable with this. Well, there's another way of identifying points in that grid. For example, let me just do it now. I'm not going to label X and Y over here. I'm just going to put 2 straight lines, just like we normally would have. And I'm going to put this out that might go, say, 1 unit. Say this is the point over here at 1, 1, which is, this graph would be right there, 1, 1. And that would have its coordinates in the Cartesian grid. So it's 1, 1. Now let's say that's the same point. Well, there's another way of actually identifying that location. What I can do is draw a line from the center over here, straight out to that point, right? And with this, there's an angle there, so there's my reference angle there, right? And that's some length, we'll call that length R. So I can go R units along the horizontal here. This is just horizontal and vertical. It's not X and Y, this is just horizontal. And here's the vertical. And then I can just rotate to theta degrees. Well, what is the length of that r, and what is the length of that theta? Well, one thing we can see for theta, since you notice right here, we'll draw it in the grid here, that angle is halfway between 0 and 90 degrees, so we know that's 45 or pi over 4 degrees. So in this case, you can see that the angle theta here, just by visualization, that theta over there is equal to 45 degrees, which has an equivalent representation in radians of pi over 4 radians. Okay, so I have that angle. What about that length r? Well, here's where we're going to go back to basic to the Pythagorean identity that we know about. And kind of drop a vertical line over here. That coordinate, this is length 1, that's length 1, that's a right angle. So I have the following, and we have Pythagorean theorem. So we use the Pythagorean theorem. And I know you've all seen this before, which if I have a triangle, you know, and that's right triangle, and this is A, B, and C, I know that C squared is the sum of the squares of the other two sides. So let's plug in. Well, we have r squared over here, that's what we're looking for, is equal to 1 squared, 1 squared, because each of these are length 1, because that's the coordinate there. So that just gives me r squared is equal to 1 plus 1 is 2, or r is equal to the square root of 2. So I could either identify this point using these Cartesian coordinates, or I could identify them using these new and different coordinates over here called we'll call them polar coordinates. So an alternative location representation is using the r comma theta value. And for that point, it's the square root of 2 comma, let me use the radian measure, pi over 4. What we've developed here is an alternative to the rectangular coordinate system, and these are what we call a polar coordinate system. We will look at this a lot more in the course, but I just want to end here and then quickly give you the homework. So we've introduced something called polar coordinates. And instead of x comma y, it's how far I go out and at what angle do I go. And instead of just having 2 lines, it looks like this. I'll put 2 over here, but then you have different lines going this direction, different lines going this direction at different orientations. So these are measures of the angle theta that go around. And then in addition to that, you have different radii that come out. So here's say radius 1. That's a circle of radius 1. That's r is equal to 1. Over here we have radius 2. So we have r is 2. And each of these are various theta values. This is, 0 degrees, pi over 4, pi over 2, 3 pi over 4, pi, etc. And you can keep going out. R equal to 3. So for example, if I said I had a point at the coordinate 3 comma pi over 2, where would that land me? Well, I'm on a circle of radius 3 and an angle, because my angle measurement, this is angle in, let's do it here, this is 0, pi over 4, pi over 2, 3 pi over 4, pi, etc. That would put me right at that point right there. My angle is pi over 2, so I'm straight up and down, and I go 3 units out. We now have an alternative, an equally valid way of representing points in the xy plane. Now, there are some subtleties here that we're going to explore later, such as what happens if r turns negative or something like that. So there's some subtleties here, but this is just an alternative. You can lay it right on your Cartesian grid, and it all works out. You can get the same designation, but using are in theta as opposed to x and y coordinates. So we're going to need that for next time, because then we're going to jump into this unit circle, and then we're going to define these trig functions, and then we're going to see how we can easily determine their values from the unit circle.